Okay, for a second lecture, we've got a little bit about scientific laws and theories. We just learned what science was, what scientists do, what kinds of branches of science there are. And now we've got to get into like how does science work? What is it that makes it go? So laws and theories for science are supported by experimental results. Scientists are always doing experiments. Theories are their kind of running idea of what's going on. So to be valid, a theory must explain observations, it must be repeatable, and it must be predictable. A theory is different than, like when you say, I've got a theory, that's like a guess. But in science, a theory is a time-tested explanation of what's going on. So theories can change for sure in science, and they do as you find out new information, but a theory is our best explanation for what is happening right now. So actually I'll do that one first. So theory is an explanation of how something happens based on observation, experimentation, and reasoning. That's a theory. Notice the how there, that's really important, because a theory is different than a law. In a scientific law, you've got, that's a description of something that's happened. Laws are usually represented by an equation. So an example of a scientific law would be like E equals mc squared. If I threw a pen across the room, there's equations for how far it's going to go, how fast it's going, how long it's in the air, how hard it hits the ground. With all those are described by equations, and that's like scientific law. Okay, but the theory of why the pen falls to the ground, okay, how it falls to the ground, what is actually going on, that's the theory of gravity. So that's the difference in an example. If you've got something that you can explain with numbers and you can explain with math and equations, that's a law. And a theory is more of an explanation of how something happens, not I think, oh my gosh, I said it backwards. Sorry. Law describes what's going on with numbers and equations, and a theory explains how it's happening. Okay, theories and laws are always being tested, and as a result, scientific changes occur over large amounts of time and are often small baby steps. You are witnessing the scientific theory right now as we live in a pandemic. We are learning about COVID-19 in very small fractions and very small baby steps, little increments. Okay, what we learn about it, we add to our knowledge base, and and it changes what we know about it. Okay, and all of this is done by experimentation, finding out new information, testing the new information, and fitting it in, adapting our model to make it work. That is a good example. We are living right now in this pandemic, and that COVID-19 really, what we know about it is a really great model of scientific theory. Okay, models can often represent physical events. Models in this class can range from like a computer model, like a model that predicts the weather. Like if you watch the weather tonight, they're like you're looking at future radar, what the clouds are going to look like, what the weather's going to be tomorrow. That's all a model on a computer. Tons and years and years and years of data plugged into a computer so that they can use that data to leverage what they think will happen tomorrow or the next day. And models often can be physical objects as well. Like a model of the solar system. Like you remember that classic model where they have like the actual planets, and you like turn a crank and it like rotates around or whatever. That's a good example of a physical model. Okay, but most models now are carried out on computers. Scientists use all sorts of models to study objects and events. Okay, you can't hold a water molecule in your hand, but you can model what one does based on data, and you can see how it would interact on a computer. A computer program can do it for you, and that is a model of what we know about chemistry and what we know about water. No matter what you're doing, though, you're going to be critically thinking. Excuse me. That's the ability and willingness to assess claims critically and to make judgments on the basis of objective and supportive reasons. So critical thinking is super important to this class. It's important to all science, and you do it all the time. People think, oh, I'm not a scientist, I hate science. Guess what? You're critical thinking all the time. If you're at your house and your Wi-Fi goes down, you have all these things that you do to try and fix it. You unplug the router, you restart the router, you check to see if the password is working. You do all these things that you don't even think about. That's critical thinking, a series of steps that you're doing to solve the problem. Okay, your phone is not sending a text. You do all these things on your phone to figure out, okay, why won't this text send? Why can't I have this picture? What is the problem? And you're doing like a little mental checklist in your head to see if you can solve that problem. And the way that you do that is a set of like critical thinking and steps that help you get to your answer. Okay. Scientists don't do that in the same way though. Like a scientist who studies biology might not have to make a lot of observations, but a scientist who studies nanotechnology may solve a problem by trial and error. So like, it just depends on what kind of science you're in, but all science are going to use critical thinking. Okay, we talk about the scientific method. Maybe you heard it when you were in elementary school. The scientific method, it's not as like when I was a kid, it was like, do this first and then you do this. It's like more of you're critically thinking and you have some steps, and you don't necessarily do them all in the right order, but you're doing some steps to solve a problem. Okay, and that might be collecting data, forming a hypothesis, which is your guess, testing the hypothesis, and then stating conclusions about what happens. So again, that's generally the order you do things in, but sometimes different scientists require a different order to solve things, and that's fine too. Scientific method is just a general description of what you're thinking. It's not an exact path for scientists to follow. Again, like when I was a kid, we had to like learn the steps of the scientific method. In reality, you can kind of solve things more than one way. Okay, here are some words that you're probably familiar with that maybe you've seen before. I'm guessing in elementary school, middle school. Scientists test the hypothesis by doing a controlled experiment. I guess I should say, what's a hypothesis first? Hypothesis is your explanation or answer of a thing that can be tested. So if you're like, oh, I see that the sky is blue. I wonder why that is. And your hypothesis might be, oh, well, it's probably because there's like a bunch of little blue bugs that live up there. Okay, that's a hypothesis. It's not a great one, but that's your explanation. Can you test it? Yeah, you can send like a blue bug collecting rocket ship into the sky and see what you come back with, right? So that is an explanation for something that can be tested. Hypothesis is usually associated with like the word guess. It's like, I think this is what is happening. In a controlled experiment, you're going to change all the variables except one of them. The variable is like anything in an experiment that you can change to test your hypothesis. Okay, so you think of that like kind of classic elementary school science experiment where you like grow a plant with a seed, and you like put a seed in a cup, and then you put one on the windowsill, and you put one like in a closet in your bedroom. And so there's a lot of variables for a seed to grow. There's the cup size, how much water it gets, how much sunlight it gets, what type of seed it is, how much soil it has, how far down it's buried. All those things are variables, and they can change the experiment. And you pick one of them to change, and you can only test one thing at a time. Okay, so you control one thing, and then everything else you have one thing that you change, and then everything else you keep the same. That's how you conduct an experiment. And even if you don't find out what you want to find out, no experiment's a failure. If you send up your rocket ship into space and you find that there are no blue bugs, it didn't come down with blue bugs, at least you know now that there's no blue bugs. Okay, so it's not a failure. You've ruled out one possibility. You can, as I mentioned, I think in the beginning here, every experiment can be used, the results can be used to revive your hypothesis or plan a test to address the next variable. So like every bit of information you get is important. And we just talked about this for COVID-19. We're learning things about COVID-19 every single day. It's not very new in terms of like the scientific world. It feels like we've been in a pandemic for our entire lives, but really it's been 6 months, and we've learned a lot of things in 6 months, but there's still a lot to learn about things, and those take place in baby steps. Finally, when you're doing an experiment or you want to make observations, there are all sorts of tools you can use. You've used some of these before, like microscopes you use primarily in biology, telescopes to study stars in astronomy, spectroscopes to study the light coming from something, particle accelerators to study what happens when you smash two elements together. Computers are tools that you use to like model things to make your lives easier. So there's a whole bunch of things you can use and that scientists across the globe use to make science work for them. Anyway, there is a good second lecture about what scientists do and what their like sort of their terminologies are.